The Bohr effect basically explains pH-dependent changes in the affinity of hemoglobin for oxygen. This makes it so that this molecule can pick up more oxygen in our lungs, where there's a higher pH and more oxygen, and then in like our toes and stuff where there's going to be a lower pH because we can't just like breathe out CO2, we're going to have a lower pH. This is going to reduce the affinity of hemoglobin for oxygen and allow that hemoglobin to dump out oxygen where you need it. So we talked about how hemoglobin binds with like positive cooperativity. So one oxygen binds, then a bunch bind. Well, this can be further tuned by the pH through the Bohr effect. And it happens because of changes that actually happen in the molecular level, with protonation offering up additional binding opportunities between the hemoglobin subunits. So really, really cool stuff. We'll talk about that. We'll talk about like carbon monoxide, not so cool stuff, and things like that. So let's dive in. So remember, hemoglobin, that's our protein that is going to carry oxygen throughout our blood. It's a heterotetramer, so it has 4 subunits, 2 alpha subunits, and 2 beta subunits. And each of those is going to hold on to a heme, which is going to hold on to an iron, which is going to help it bind oxygen. Now, because we have those 4 oxygen binding sites, we have 4 opportunities to bind oxygen. And what happens is that the first opportunity is going to be a lot harder than all the subsequent ones, because hemoglobin demonstrates positive cooperativity. So once one of the oxygen binds to one site, it's going to make it easier for oxygen to bind to the other site. As a consequence, what's going to happen is we get a sigmoidal binding curve, even on a linear scale, where at higher oxygen concentrations, which is often measured as partial pressure, you're going to have a higher affinity, and so the hemoglobin is going to bind more. And at lower oxygen concentrations, you're going to have a weaker affinity, and so the oxygen is going to bind less. You're going to offload the oxygen where you need it and take it up where you have a lot of it. Remember our key terms. We had allostery. That was something that happens at one location of a molecule, such as the binding of oxygen to one of the sites, that affects what happens somewhere else in that molecule, such as making the hemoglobin change shape so that those other binding sites have a higher affinity. We can use the term modulator to describe a ligand, so a binding partner that causes allostery and affects the binding of ligands. This can be negative, which would mean that its binding decreases affinity for subsequent ligands, or positive, whereas it increases the affinity for subsequent ligands to bind. We further described how we could refer to these as homotropic if their modulator affects the binding of a copy of the same ligand, or if it was heterotropic, so it affected the binding of a different ligand. So what type of modulator is oxygen acting as? Oxygen is going to be acting as a homotropic positive modulator. Homotropic because it's affecting the binding of subsequent oxygen molecules, and positive modulator because the binding of one oxygen molecule increases the affinity for further binding. We saw how this came down to structural changes in the hemoglobin protein. Hemoglobin has those 2 main states, the T state, the taut state, and the R state, the relaxed state. So remember, the relaxed state is going to be the state that binds to oxygen. Think R, think of red, think of the oxygen being red. So that R state is going to be that's bound to oxygen. You can also think about like you're more relaxed if you have oxygen, right? So this is going to be the relaxed form. It's somewhat confusing looking because what's going to happen is you kind of have it more condensed looking in the relaxed form than in the taut form. But the taut form is called taut because it's going to involve more of these salt bridges between the different subunits, but it will have a bigger hole in the central cavity. But the taut stage, this is basically your weaker binding affinity, and then the relaxed stage where you have a higher binding affinity. And what happens is that when you bind that first oxygen, you stabilize the R state, making the higher affinity for the subsequent sites to bind. As a result, in your lungs, where there's lots of oxygen, you're going to be in that R form. And then in your toes, you're going to be in that T form. So if you have no oxygen, then you have a little oxygen bind. That's going to increase the binding affinity for further oxygen. So you're going to quickly saturate. Then when you're in your lungs, you're going to stay at that very high percentage. But then when you go the reverse direction, because remember this binding is reversible, well, now if you decrease the oxygen concentration to say the concentration that you would find in your tissues, well, now you're going to have a lower affinity. So you're going to end up offloading a lot of oxygen into the tissues that need it. And having this cooperativity allows you to do that. Whereas if you were only in the T state all the time, you wouldn't be able to pick up enough in your lungs. And if you were only in the R state all the time, then you wouldn't be able to give off enough in your tissues. But by having this positive cooperativity, we're able to do this. We saw how this was caused structurally by allosteric changes that occur when oxygen binds. Remember that heme has that porphyrin ring. It's kind of puckered when oxygen isn't bound, but when oxygen binds, it kind of flattens it out. And when it does this, it kind of pulls on the amino acids that are making contact with that iron. And so it's going to pull this alpha helix, which is going to pull the stuff that's around it. And as an end result, you get this conformational change where the entire protein is changing shape. So remember that this protein kind of all folded up all nicely, and now you're making a change, and so the protein has to adjust. It happens mainly through these few key residues like histidines that are interacting with that lysine. But bottom line, you end up with this T form and this R form, and these different forms are going to have different affinity for oxygen. So basically, you bind to the oxygen, you cause that pulling, you change the shape of hemoglobin. This makes it so that the other oxygen binding sites have a higher affinity for further binding of oxygen. But if you release that oxygen, well, now what's going to happen is you're going to get shifted to that top form. In that top form, you're going to have the salt bridges form that we'll look at. And then this is going to stabilize this form that has a lower affinity for oxygen. So you only need that single binding event to help shift the balance and stabilize it in one form or the other. So if you bind one oxygen, you quickly transfer into the state that you can bind more oxygen. But if you release one oxygen, you get to the T state where you're going to release more oxygen. Exactly what we need. And when we're in this mid-range, small changes in PO2 can make a big difference. So even if someone has low oxygen, we can give them oxygen and quickly help restore oxygen in their blood. But we'll talk about some things that can actually prevent this, some medical consequences, things like carbon monoxide poisoning. So we talked about how oxygen was going to be a positive homotropic modulator. But then we talked about another modulator. We talked about a modulator called 2,3-BPG or 2,3-bisphosphoglycerate. To review, 2,3-BPG binds to the central channel that's open in the T state, which is the low affinity state, but not the R state, the high affinity state. This binding stabilizes that T state, which is decreasing the affinity for oxygen, shifting the curve to the right. This is responsible largely for enabling the cooperativity of hemoglobin, that positive cooperativity, where the oxygen binds to one site and quickly the rest follow. And when oxygen unbinds, the rest unbinds. So what type of modulator is BPG acting as? So BPG is acting as a heterotropic negative modulator. Heterotropic because it's affecting the binding of a different ligand. So BPG binding is affecting the binding of oxygen, and it's a negative modulator because it's reducing the affinity of oxygen. And this has important consequences, and it helps our bodies further fine-tune the amount of oxygen that is bound by hemoglobin. So we saw how we had oxygen acting as a positive homotropic modulator and BPG acting as a negative heterotropic modulator. Now let's talk about a different way that we can affect affinity, and this is called the Bohr effect. So it was originally described by Christian Bohr with Hasselhoff and Krog in 1904, and the original paper is in German, but you can find a translation of it that I can link to. What they found was that you got a change in the affinity of hemoglobin for oxygen depending on the pH. More specifically, at a lower pH, there was a lower affinity for oxygen, whereas at a higher pH, there was going to be a higher affinity for oxygen. So in black, if you just have normal, if you then lower your pH, you're going to get a shift to the right. Remember that a shift to the right is basically saying you need more oxygen for half of it to be bound, whereas a shift to the left is saying you need less for it to be bound. So at a lower pH, we have a lower affinity, and at a higher pH, we have a higher affinity. And remember that even little changes in the numbers for pH can correspond to big changes in the amount of protons available. So this can actually have a pretty dramatic effect, even for small little changes in the pH. So to understand why this is actually happening, and we want to understand why this is happening because it's super duper freaking cool, the Bohr effect is going to involve interactions between the alpha and the beta chains that are going to help stabilize the top form and be pH dependent. What happens is that in the T form, you're going to have salt bridges. So remember, those are ionic bonds that are going to form between the chains. So remember, we have those alpha and the beta chains. What we're looking at here is part of one of the beta chains. And this His 146 is going to be the C terminus. You don't need to know all the names of all of these, which specific ones are interacting. This is more just to kind of like give you a look at the actual biochemical molecular basis for physiological things that are super duper important to real life. So again, don't worry about all these details, but just kind of try to take it all in, how awesome it is. So this is the C terminus of the chain. Remember, that's like the end of the chain because we talk about proteins as going from N to C terminus. Over here, there's going to be this aspartate 94. Aspartate, remember, that's one of our acidic amino acids, and histidine, that's one of our basic amino acids. So the two of these can form a salt bridge. And what this is going to do is it's going to orient the C terminus of that beta chain towards a lysine on the other chain, so on the alpha chain. So you have this lysine sticking out, and then you have the C terminus that's directly oriented to form a nice salt bridge with it. So you get a salt bridge here that helps orient you to form a salt bridge here. But remember that histidine, it only had a pKr of about 6. And so it was predominantly going to be in its neutral state. And so in order for this reaction to actually happen, though, histidine needs to be in its positively charged state. So if there aren't enough protons around, then you're not going to get this BB interaction. And what's going to happen is that the histidine is going to be too far away. So even though it's got its C terminus, it's like all the way over here, as opposed to over here where it needs to be to interact with this lysine. Now you're all the way over here. That is not going to be able to form a salt bridge. So in that R state, you're not going to be able to form that salt bridge, but in the T state, you are. But in order to form that salt bridge, that histidine has to be positively charged so that it can then interact with this aspartate to position that C terminus to interact with the lysine. So basically, in the top form, you can have these interactions form, but they depend on histidine being protonated. If histidine is not protonated, you can't form those stabilizing interactions between the chain, and so you end up being in the relaxed form.
So let's take a look at this in 3D. So remember that when the oxygen binds, you get that conformational change. You get that porphyrin ring flattening, drawing the histidine with it. That histidine is attached to a bigger protein. And so what's going to happen is you're going to pull the whole protein along with you. And so oxygen binds R, unbinds T, R and T. And we've got our beta chains and our alpha chains. Keep a look at what's going to be happening around here. So no oxygen with oxygen. No oxygen with oxygen. You can see these kind of termini are moving. Now, if we look and actually look more closely, we can see that what we were seeing there was that histidine C terminus. And so the C terminus is negatively charged, but the histidine is positively charged at low pH, but not at high pH. When it's protonated, it's going to be able to form a salt bridge with this aspartate, and that's going to orient the C terminus in order to form a salt bridge with a lysine on this other chain. If we look at our coloring, we see that the alpha and the beta, so this is the alpha, this is the beta, and then this is an alpha, and this is a beta. So the darker ones are going to be the beta. So this is the beta, and we're looking at the C terminus of the beta, going to be making an interaction with this lysine in the alpha, these salt bridge interactions. If we go closer, what we can see is that, so let me show it in stick view. So here is what we were looking at before. So we've got this histidine. So this part of the histidine is positive at a low pH, and this is the carboxyl terminus of that histidine, so of the whole chain, because it's the last part to do with the chain. And so you have the C terminus and you have your carboxyl group, and the carboxylic group is going to be negatively charged even at the low pH because it has such a low pKa. So it's going to be able to form a salt bridge with this lysine. And this histidine, however, in order to have that C terminus oriented that way, it needs to be making a salt bridge to this aspartate. And in order to make that salt bridge, the histidine needs to be positive. So we need this to be positive in order to form this interaction. And we need to form this interaction in order to orient this tail so that we can form this interaction. And if this is deprotonated, you don't get this salt bridge formation. So the C-terminal tail, the carboxyl group of it, is not going to be oriented towards this lysine. So we've got oxygen bound R, unbound T, bound R, unbound T. It's that unbound T where that tail is going to be making that salt bridge. And that salt bridge is only going to be makeable if that histidine was protonated. And that histidine is likely to be protonated at a low pH, but not a high pH. And so we need low pH, such as what we get with CO2 production that leads to that lowering of the pH, the increase of the proton concentrations. The higher proton concentrations, the histidine gets protonated. The protonated histidine then coordinates with the aspartate, making that ionic bond with the aspartate in that same chain to orient the tail of it to make a salt bridge with this other chain. And once you make that salt bridge with that other chain, once you're in that top formation, you're actually going to be opening up a channel, and that channel is going to be where the 2,3-BPG could bind. So 2p3bg is only going to be able to bind there when you have that channel opening, and that channel is only going to be opening in the top state. So it's a little confusing because it changed the view on us. But what we're looking at here is going to be that 2,3-BPG binding site.
So what's going to dictate whether histidine is protonated or not? Well, that's going to be its pKa and the pH. So remember the pKa, we talk about approximate pKa's, and you can find those in a table. So remember, we can also refer to a pKa for a side chain as a pKr. So histidine is traditionally about 6, which means that at a pH of 6, half of it would be in its protonated form and thus positive, and half of it would be in its deprotonated neutral form. If we're at a pH of 7.4, so basically most of it is going to be in its neutral form, which isn't going to be very useful to us. But if we can raise that pKr, what that means is that most of the time we're going to be at a pH that's under that. So most of the time we're going to be protonated. So we'll increase the amount of protonated. We can also increase the amount of protonated by making there more protons available. So if we decrease the pH, make the solution more acidic, we'll have a higher likelihood of finding more of the histidine be in that protonated and positive form. And so we're going to be able to do both of these things. So we have our aspartate. And remember, our aspartate is negatively charged. So how do you think it might affect His 146's pKr? Is it going to raise it, lower it, or have no effect? Having that aspartate 94 is going to raise the pKr of histidine. Basically, it's going to stabilize that positive charge on the histidine, make it happier to have that proton, and therefore less likely to give it up, more likely to take it, less likely to give it up. What does that mean? We're making it a worse acid and a better base, so we're going to be raising that pKr. So this is going to make it so that histidine is easier to protonate, but it still needs to have protons available. And so where are those protons going to come from? The bloody bicarbonate buffer system. You don't need to know all the details of this bicarbonate buffer system, but your body has ways to control the pH of your blood and of your everything. And one of these main ways is through the bicarbonate buffer system. What happens is that when you have CO2, such as can be released when your cells are doing all their energy making, so we have cellular respiration, which we'll talk about a lot more, but basically there's this part of it called the citric acid cycle. And in that citric acid cycle, you're going to be releasing this carbon dioxide. So when your tissues are working hard, you're going to be producing carbon dioxide. This carbon dioxide is then going to react with the water with the help of this super duper cool enzyme called carbonic anhydrase. That carbon dioxide is going to react with the water to form carbonic acid and bicarbonate. And so, fun fact, carbonic anhydrase is one of the speediest enzymes known. It can combine CO2 with water to make carbonic acid or do the reverse 1 million times per second, which is 10 million times faster than it would happen on its own. So hope this gets you excited about our upcoming section on enzymes, because this is just like one of the coolest ones. But anyway, the significance of this is that when that carbonic acid deprotonates, it releases protons. And when we have more protons, well, now we lower the pH. Your body has ways to compensate in order to keep it steady by like changing the breathing and the kidneys in order to compensate. But what we really care about for our purposes here is that you have water react with carbon dioxide to give you carbonic acid, which can deprotonate to give you bicarbonate, producing protons. So more carbon dioxide, lower pH. And the significance of this is then remember that when we have that lower pH, there are more protons available. If there are more protons available, then our histidine is going to be protonated. If our histidine is going to be protonated, then it can form those salt bridges that stabilize the T state. And this is going to then promote the offloading of oxygen. And this is really, really great because, well, in our lungs, say we have plenty of oxygen and we're able to give off the CO2 because we can just breathe it out. But if we're down in our toes where we have a lot, we're doing a lot of energy making and producing CO2, but we can't just like breathe it out of our toes. Our CO2 is going to build up. We're going to get a higher proton concentration. That's going to protonate the histidine, going to make it so that you can form those salt bridges, stabilize that T state, and dump off the oxygen. Then when that hemoglobin goes and it travels back to the lungs, well, now there's going to be less CO2. Without the CO2, now you can't form those salt bridges. You have a higher oxygen, so you can bind to oxygen. Once you bind to oxygen, well, now you're quickly going to stabilize that R state and increase the affinity, allowing you to uptake oxygen. Remember, T state is going to be that taut state where each time oxygen and hemoglobin meet, they have a lower probability of sticking. So they need to meet more in order to get the same amount of binding. So you get your curve shifted to the right. In that R state, however, they're more likely to stick each time they meet, so they don't need to meet as much in order to get the same amount of binding. So this is going to be shifted to the left. And this could be explained in terms of those histidine being protonated and allowing it to form those interactions, but that's actually only part of the story. CO2 is actually also going to kind of directly stabilize things by offering up new opportunities for salt bridges to form where they wouldn't normally. So basically that carbon dioxide can react with the amino terminal residue, and this can make a carbamino terminal residue. So you're taking what was like a positively charged N terminus and you're turning it into a negatively charged site. When you have something negative, well, now it can form a salt bridge with something positive. So what's going to happen is that then you can get a new salt bridge forming that you wouldn't have had before. And at the same time, you're going to be giving up a proton, you're going to be lowering the pH. So the bicarbonate system is only like one of the ways. It's the main way that your body like transports CO2, but the other way is through hemoglobin itself. So with reacting with hemoglobin, you're releasing more protons and you're kind of making it so that there are additional interactions that can form that stabilize that T state. Fun fact, like hyperventilation, you know how they say to breathe into a paper bag? Well, there's actually a biochemical reason for this. What happens is when you hyperventilate, you're breathing out too much CO2 without taking in enough oxygen. Without that CO2, well, now you don't have that pH lowering, and without that pH lowering, your hemoglobin isn't going to shift to that lower affinity state. And so you're not going to be giving off as much oxygen as you need in your tissues. But if you breathe into a paper bag, what's going to happen is it's going to force you to rebreathe in that carbon dioxide, allowing that to then lower the pH, allow those salt bridges to form, and stabilize that T state that's going to release the oxygen where you need it.
What if you can't go through the citric acid cycle? So maybe there's no oxygen, or maybe you're in erythrocytes, red blood cells, where they don't actually have mitochondria, which is where the citric acid cycle takes place. Don't worry, they can still make 2,3-BPG. So remember that 2,3-BPG could be made as like a bypass way of part of glycolysis. So if you're doing a lot of glycolysis, you can make more 2,3-BPG, and that 2,3-BPG will act as that negative modulator, and it'll help you still be able to deliver the oxygen. And that would be really important if you didn't have oxygen, which is why you were doing glycolysis and you were doing anaerobic respiration rather than going through the citric acid cycle. So more on that later in the course, all that respiration stuff. But for now, just focus on the 2,3-BPG and the carbon dioxide. One more fun fact about hemoglobin before we get into the not so fun things like carbon monoxide and sickle cell anemia. You might have heard commercials about HbA1c, maybe diabetes commercials, and they're talking about HbA1c levels or saying, ask your doctor about your HbA1c levels or something like that. HbA1c refers to hemoglobin, the beta chain, where the N terminus of it has been glycated. And so glycation, we see that prefix glyc, that's telling you sugar. And so glucose, our blood sugar, it can actually react with the N terminus of the beta chain, and it can form a covalent bond. And so we call this glycation, and we call it glycation instead of glucosylation when it's just happening non-enzymatically. So you don't need to worry about that. Just know that glucose is going to be able to form a covalent bond to the end of the beta chain. Because it's a covalent bond, it's not just going to fall off. And because hemoglobin can stick around in your body for about 120 days, the higher the blood sugar levels are, the more likely you are to be glycated, and that glycation sticks. So over time, you're going to build up this glycated hemoglobin, this HbA1c. And so when doctors want to know a patient's blood sugar levels over time, rather than in this moment, they can look to the HbA1c to see how much glycated hemoglobin there is. And that's a longer term readout about control of blood sugar levels, as opposed to just doing a finger stick or something to see what the blood sugar levels are right this minute. So both are important pieces of information, but longer term information can be gotten by looking at the HbA1c levels. And if it's high, that indicates that there's a lot of glucose around, because that glucose was then able to interact with the hemoglobin and to form these covalent bonds that left the evidence that the glucose levels were high in the last 2 to 3 months. Okay, so that was like cool stuff about hemoglobin. Let's talk about some of the not so cool stuff, or I mean, some of the bad things that can happen. One of the worst is binding to carbon monoxide. So we are not talking about carbon dioxide here. Carbon dioxide was helping us before. Carbon monoxide is not going to help us, like, ever, which is why we have to have carbon monoxide sensors in our houses. Carbon monoxide is a whole different beast. It actually binds in the same place as oxygen, so it directly competes with oxygen. So it's not acting like one of the BPG where it's binding somewhere else but affecting the binding of oxygen. It's actually competing for the binding of oxygen, at least at one subunit. But it has the same effect in terms of then it's going to stabilize the other subunits in that form that has a high affinity for oxygen. And so you're going to pick up a lot of oxygen, but then you're going to have a really hard time letting go of that oxygen, because that carbon monoxide is going to bind so tightly that it's going to be really hard to release it. And so you're going to be stuck in that relaxed form. Think about how would carbon monoxide affect the binding at that site, and how much oxygen could bind to that site, and how it affects the binding at the other sites. Let's see what that would look like on a curve. So say we had 50% carbon monoxide bound hemoglobin. We can see that our total saturation, so the proportion of hemoglobin that's bound by oxygen, we're up to 50%, because 50% of it is taken up by the carbon monoxide. We can also see that we've lost that cooperativity. So we've lost that cooperativity basically because when the carbon monoxide binds, well, now you're not able to have that cooperative effect where an oxygen unbinds and then the rest unbind, because that carbon monoxide is kind of locking it into that higher affinity conformation. But the total amount of hemoglobin that you can bind is still less. And so you are barely releasing any oxygen in the presence of the carbon monoxide, and it's really hard to get rid of because it's binding so tight. And so that's why carbon monoxide poisoning is a really bad thing. Speaking of anemia, sickle cell anemia. This is a disease caused by a mutation in the hemoglobin protein, and it's this E6V mutation.
So what does E6V tell us? Remember how we talk about mutation? It's going to tell us that the 6th amino acid in the hemoglobin chain is swapped from a glutamate to a valine. Now, what do we know about these amino acids? How do we classify glutamate? Glutamate is an acidic amino acid. It's hydrophilic, it likes hanging out with water, and so it would be happy on the surface. What about valine? How do we classify valine? Valine is one of the nonpolar amino acids. It's hydrophobic. Normally, it's found somewhere buried in the center of a protein. So what's going to happen if we change something hydrophilic and charged to something hydrophobic, nonpolar? Now what's going to happen, you put this nonpolar thing on the surface of a protein, and it's not going to be very happy. But if it finds another nonpolar patch on another hemoglobin unit, well, then they can link together. And so you get these abnormal hemoglobins that link up to form long fibers. These can then twist together in long helical structures that cause red blood cells to get misshapen and clog blood vessels. This polymerization is favored in the low oxygen state. It's easier for those interactions to be made in the low oxygen state. Remember, that's our T state. So as the cells are going to go like cycling throughout the body, they keep polymerizing and unpolymerizing over and over again, majorly stressing out the cells. So this is what happens with sickle cell anemia.
Go ahead and look at the site of the sickle cell hemoglobin mutation. And so this is going to be here. This white is going to be the hydrophobic patch that's exposed in both the normal and the sickle. However, the mutant has another hydrophobic residue, this valine here. And this valine is going to be on the surface, and it's going to be able to interact with a hydrophobic patch on the other copies of hemoglobin. So not that same hydrophobic patches was formed by the valine, but that other hydrophobic patch. This is going to be allowing them to link up. And this is going to be exposed predominantly in the deoxygenated state. And so this is going to make it so that you get this clumping in the deoxygenated state. So when there's low oxygen, you get the clumping, and there's going to be low oxygen in like those veins. And so it's going to clump up in the veins and cause these chain formations that are then going to occlude the blood vessels.
Review hemoglobin. So remember, it's got those 4 binding sites, and it binds with positive cooperativity, meaning that if one oxygen binds, then the rest of them are going to bind quickly. And if one lets go, then the others are going to quickly follow. As a result, you get this sigmoidal binding curve. Sigmoidal even on a linear scale, where at higher oxygen concentrations, you're going to have a higher affinity for oxygen, and at lower oxygen concentrations, you're going to have a lower affinity for oxygen. As a result, you're basically able to take up oxygen in your lungs and release it in your tissues. This is helped along by the Bohr effect. The Bohr effect is going to be this pH-dependent effect, where you're going to get stabilizing salt bridges form that stabilize the top phase, which is going to be that oxygen offloading phase, that low affinity phase. Those are going to be dependent on a histidine being protonated, and that's going to be dependent on how many protons are around. Well, how many protons are around? That's going to depend on the pH, and the pH is going to depend on how much carbon dioxide there is. The more carbon dioxide there is, the lower the pH, the more you stabilize that offloading state. And where would you find these conditions? Well, you would find them in tissues that aren't able to expel carbon dioxide easily, but are producing a lot of it and don't have much oxygen. So that was where you would find this in the tissues where you need oxygen the most. You need it to be offloaded the most. So that's perfect. In our lungs, we've got plenty of oxygen. We're able to expel out that CO2 easily just by breathing it out. So we're going to have a higher pH. We're going to be stabilized in that oxygen-loving R form, going to allow us to take up the oxygen without giving it off too soon. So at a lower pH, which we can get by having a higher CO2, we have a lower affinity for oxygen. And if we have a higher pH, we have lower CO2, we have a higher affinity for oxygen. A key thing to keep in mind when you're trying to figure out what way the regulation should go is that if you want to release oxygen, you need to lower the binding affinity for oxygen. So it can seem a little counterintuitive, like you need oxygen, so you want to make it bind less. But yes, you want the hemoglobin to bind less so that it's actually releasing more.
If you're saying that you have a lower affinity for oxygen, basically you're saying you're better at releasing the oxygen. And if you had a better affinity for oxygen, you'd be worse at releasing it. So if you want to release oxygen to your tissues, you're going to need to have a lower affinity for the oxygen. Two ways we can actually lower that affinity are with our allosteric modulator, the 2,3-BPG, as well as with the Bohr effect. And then we have the fact that the oxygen itself is also going to be helping regulate things because of its allosteric nature. In that case, though, we have a homotropic modulator because the oxygen is affecting the binding of further oxygen, rather than heterotropic, such as in the case of our 2,3-BPG, affecting the binding of oxygen.